lessons learned from across the diverse matrices. This will be presented by Dr. Angela María Fasnacht. She's a Ph.D. PE fellow and faculty from Princeton University and advisor to Komline. Very pleased to have you here today with us. Thank you.
Okay, well, let's get it done. Let's get it happening toward the end of the afternoon. So wake up, everyone. All right, clicker, and so for today, I'm going to go over quickly some of the background of PFAS, but everybody probably know this very well. Regulatory slides, in addition to drinking water, I have a couple of other ones that may be useful for you also to see. Quickly, I'm going to go over that. I will go over the PFAS kit. It's a Komline PFAS kit. I'm collaborating with the Komline company to develop it for a drinking water PFAS end-to-end process. And within that kit, we have different technologies. And so for each one of these stages, I'm going to go over some of our lessons, our processes and findings. So everybody knows PFAS, so I'm not going to repeat all of this. Super persistent, widespread, is everywhere. The key here that probably was mentioned this morning in one of the presentations is the definitions. PFAS definitions seem to be very different across the board. US EPA has some sort of a definition. TSCA has also from EPA has a different definition. EU, different definition. And that makes a big issue because it will add up more PFAS to treat or less PFAS. For instance, the definition from EU will definitely include probably 10,000 PFAS to not have and remove. But the definition that we have today for EPA is based on compounds, and so we have the 6 that we need to focus on in drinking water, for instance. At the state level, that's another thing to consider, because at the state level, we do have states like California that do have similar definition as the EU definition, which is basically stating that they are going by any fluorinated substance that contains at least one fully fluorinated group. So that really defines basically everything PFAS, no? So in terms of the life cycle, yes, we know that it's everywhere, and everybody knows that now. And what is important here is that because we are required to remove based on the EPA standards, we also need to know that we are, at this point, our own acts could possibly be moving our PFAS everywhere else unless we have a final destruction technology. So we know that current solutions like disposal, incineration, and many others could redistribute PFAS or even crack PFAS into transformative products. So I'm so glad to see Veolia's results, to see, I'm looking forward to seeing more results like that and making sure that our transformation products stay put. So the compliance, as we know, we have, this is April 10th, 2024, we had EPA promulgated the drinking water rules. That means that 2024, 2 years from that point, everybody should have a solution in mind. A year later, we'll have to start notifying you and me if we have PFAS in our tap, and a couple of years after that, 2029, utilities will start receiving NOVs, notice of violation, when PFAS is found and haven't been treated. So get ready for those notifications, because it's really a short time for you to be able to react to all of that, but it's needed. Now, the 2025, like today, this year, that's an intrinsic deadline for state revolving funds and for grants that may have been at the hands of states to support utilities that need that that boost for treatment. Those are the couple of slides that would be helpful too. I'm not going to deep dive into landfilling and wastewater and other consumer products, but even though EPA only have the drinking water standards as the promulgated rule. There are other rules that are going on at the state level for landfilling and for wastewater and for consumer products. So states like Maine, everybody knows because that was in the news, early in 2022 started considering how to control leachate from landfills, and also is already making sure that land application of biosolids that contain PFAS is not allowed. It's not the only state. Connecticut follows, Michigan, Oklahoma, Mississippi, and Texas. There are many others to come. That extracted information from common requirements is something that's coming from Michigan. Currently, Michigan is making sure that at the wastewater side, the wastewater treatment plants have a limit on PFAS effluent disposal, PFAS effluent. And what they do, they instituted as part of their industrial pre-treatment program, included PFAS as part of their constituencies to monitor. So they do their own monitoring process as well. This is a quick table about consumer products across the country. States are really moving into monitoring and controlling PFAS on their own as well. Okay, so getting into the drinking water, what we have, and my life has been mostly in operations, and I had the opportunity to be able to collaborate with Komline into developing this PFAS kit for drinking water. So Komline has an arm that owns also membrane technologies, a membrane skid, work with different membrane manufacturers. So the heart of this skid is the membrane, could be RO, it could be nanofiltration. And the idea across that is that we built a wholesome solution, a solution where our clients don't have to deal with multiple vendors, or they don't have to go through different technologies. They just handle, in one single stop, everything, and have our water ready to fulfill with any regulations. So the skid has water quality monitoring, making sure that we have ports to be able to control monitoring and also to know that we are at stake with the regulations. It does have the membrane technology that is the hardcore of the entire process. Membranes can remove 90% of PFAS in one single pass. It has a PFAS selective adsorbent. This one is a polisher, so it's basically acting as a polisher for the drinking water. And for the concentrate, that sometimes everybody asks, what happened with the concentrate? Concentrate, we are having the foam fractionation, one of the foam fractionation technologies that we built, so that we can reduce the volume and help with the downstream selecting the technology for destruction that will be more cost effective because of the volume downsizing. So let's go over some of these technologies. So the first one, membrane, this is some fundamental principles of membranes. Membranes, but specifically for PFAS, they do have a great percent of removal, like 90% of removal, especially for RO. So right there, I actually had I was very pleased to hear some of the locations that I've been working with. They do have PFAS in the influent in the drinking water, but because they have RO without even knowing, they're able to remove most of the PFAS that we are mandated to remove, with the exception of some short chains, and that's understandable because of the molecular weight. So the membranes also could work well because in RO they interact well with nitrates, for instance, remove nitrates, and it's able to work in groundwater and surface water, and it really controls a lot of disinfection byproducts that are such a big problem. Key of membranes is that everything goes by molecular weight and not by concentration of the contaminant, and so any type of concentration it can be treated with the membranes. In this case, this study reviewed one particular constituency that it may be of interest, which is the natural organic matter. natural organic matter and understanding how that competes with the PFAS removal. So in this case, it was shown that it actually helped in the rejection process. And most likely this is due to the absorption process and maybe the site exclusion. And that is a positive element because that means that, the multiple PFAS can really work with the NOM and the surrogates to be able to exercise better rejection process. However, it's always important to understand what type of pretreatment process we need to use for membranes because, although this is a positive part, there are other solutions that may need to require removal of water hardness, and that means that in some situations we need to use UF. In this one, the analysis was done with RO and nanofiltration. RO is the solid circles, and the nanofiltration is the not solid circles. So on this one, the analysis was done with two different types of, the idea is to focus on the molecular weight. So the analysis was based on molecular weight. Longer chains have typically higher molecular weight than shorter chains. And so the review was basically to focus on analyzing whether it was equally removed longer chains versus shorter chains with the two different type of membranes. So it is proven now that indeed molecular weights that are less than 400 Daltons, maybe 300 Daltons, may be a challenge to some membranes, type of membranes, like probably some of nanofiltration mainly. RO, as you can see across the board, perform very well with those shorter, smaller molecular weights. Temperature is another part to consider with any treatment using membranes, especially for PFAS. At higher temperature, the permeability increases, and at lower temperature, it can reduce the membrane efficiency. And so it's important to be able to balance the diffusion and separation opportunities in there. In here, we tested the hollow fiber nanofiltration membranes. There were two types of membranes and two different waters. One was surface water, one was effluent from wastewater. And I'm bringing effluent wastewater because again, as I started to work in thinking about membranes for PFAS, there was a lot of great experiences where people had, by chance, a membrane technology after the effluent, and that ensured them not to have PFAS in their effluent at the end. So that was a positive part. For this particular test, surface water, as you know, it has high natural organic matter and low dissolved oxygens. Effluent has high dissolved organic content, salts, and contaminants. So for the case of one of the DN40, they were very consistent across the spectrum with great removals, removals from 70 to 60%. That's, talking about surface water, that's great for the performance. For effluent, it was not as efficient, but it still was good enough. And most likely wasn't for effluent water. We need probably another type of technologies in terms of the membranes because of the organic content and the ionic strength. Generally, that was in competition with the PFAS. For this last slide on membranes, the test was done on 3 different categories. One was the macro parameters, conductivity, pH, and then thinking about the ions, so calcium, sodium, sulfate. So for divalent ions, calcium and sulfate, there was a great removal, and that's what we need to remove. For monovalent ions, the removal wasn't as much as good, but we don't need to remove those in drinking water, so we're okay. Then in the middle chart that you see in there, those are the aesthetic parameters to consider. So color, TOC, DOC. It really performed very well on these removals, some of which arrived to up to 90% removal. So that is very important because it really reduced the chances for disinfection byproducts formation, as well as improve the aesthetics of the water and support the biological stability. And the last table, that is all about heavy metals. So it's important to know that because there are many groundwater sites where there is PFAS and there is arsenic. And arsenic, for instance, was one, so aluminum and iron was one of the ones that were removed very efficiently. Arsenic was next in line. And so that's very, very good to consider as well when considering the membrane technologies that we're going to use. So that is for the part of the membrane. So in the skid, as I mentioned, that goes by what type of really PFAS we're going to treat, right? And how is my water characterization? That helps with the selection of the membrane to choose. Next is going on the polishing step. So as I mentioned, the performance of the membranes is great for longer chains. There are some short chains that are not as great, right? So the polishing step includes the fundamental of adsorption, and basically in this case, it is, is using the hydrophobilicity of the PFAS in different chains and different components, and then the type of media that we're going to use or that as part of the adsorption process. I listed here a lot of materials for media. There are many types of medias, and we have seen many of them presented today or even at the exhibiting hall that work well with certain kind of PFAS type, and that's also depends on what type of water we're putting the PFAS is on, right? For our case, we have selected a PFAS adsorbent from it's called Puratech 400. And the reason we selected this one is because it does have a very rapid effect. It has a shorter empty bed contact time, sometimes even less than a minute to be able to go through, and this is even using it directly, not after the RO. And it does have, is made cater for PFAS in particular, not necessarily for any other contaminants, just focus on PFAS. It does have a porous structure that really helps to be able to trap the PFAS, as well as the coating that helps to do that adsorptive process. So this can tell why that was the reason to select this one to work with. These comparatives is against all, an ion exchange media, and as you can see in the left chart, the resins took just at the 60,000 bed volumes, we could see a breakthrough. Meanwhile, the media, the G400, continue and then didn't, it's the purple line, and it just continue performing. So that's a great result. That one has only one type of PFAS. The table on the right, the chart on the right, there are multiple PFAS in it, 4 of them, and it's still, again, the ion exchange breakthrough earlier, and the purple line, which is the G400, performed much better. In essence, it's because of that ability to be able to be focused on a specific type of media. So this completes the polishing process after the RO treatment to be able to ensure that shorter chains also are taken care of. By the time that the process leaves the system, it's already ready for drinking water standards. So the next one is the concentrate. Membranes produce concentrate. And so how we decided to focus on that, as I mentioned before, is using foam fractionation to be able to further concentrate, deconcentrate. And you probably saw foam fractionation processes presented today, very good technologies. The way that we have designed the foam fractionation is catered to this PFAS. Which PFAS? The PFAS that are in the concentrate of the membrane, which most likely are the ones with the higher molecular weight, the longer chains, because that's how RO traps the type of PFAS. So in terms of the performance, in here we can see different type of surfactants. The cation surfactant behave much better probably because of the ionic properties of the PFAS. And we can see that, again, longer chains are much better than shorter chains, and that's something expected as part of the process. The final step that we are at is on the destruction technologies. There are many removal and destruction technologies. I have classified all of them, or this is one of the classifications found in the literature. There are 3 different types of technologies for removal and destruction. Here, the physicals that you can see here is everything that probably we have seen so far: ion exchange, AAC, that sort of media, membranes, filtration, all of that. None of that destroys. The chemical group that you see here is what still is being under development, but could be promising for destruction. We are in the process of selecting one of those, and the next time we have the chance to present, we will have the results of that one. And the final one is another one that is in less at the product level and readiness, but is very promising as well, is the biological destruction process, because it really uses bacteria or uses algae or uses the ability of the plants to be able to get and collect properties, chemicals or elements like PFAS. I will skip that. So as a general takeaway from today and from of this process is that it is important to know that the system that we need to define and design a smart system is a system that has the right material selection and it is effective for PFAS, if that's our goal, right? We know that long chains are easier to remove across the spectrum. Short chains and emerging compounds will require some specific solutions. We need to think about that. Integration is key. One single element is not doing it. We need to integrate, and we have elements to be able to do that. The modular treatment processes is a very great opportunity to be able to scale up and be able to work with multiple systems to be able to cater for the right type of water matrices that we're using. And of course, always keep in mind that there is always a pre-treatment opportunity in these situations. Thank you.
Any questions? There we go.
Thank you. I have 2 questions. First one is, what was the recovery on that membrane that you studied? And the second question is, why did you not consider sending that concentrate from the membrane directly to the destructor? Was there any specific reason why you considered foam frac in between?
I couldn't understand. I'm sorry, we couldn't understand the question.
It's not you. It's not you. I mean, even the last, I was surprised,
I can repeat
right?
that.
We were like, how can you understood, but I couldn't, we couldn't. Yes.
I can repeat that. Yeah.
Maybe
so the first question is, the recovery of, membrane. Like, what was the recovery in the process? How much water you were able to recover through that membrane?
How much water?
Yes, you were able to recover. There is you are generating concentrate from the membrane, right? So what percentage of your feed water was going to the waste? Was it 80% recovery or 90% recovery?
Okay, I'm really having a hard time. So your question is how much water? And again, excuse me, it's not you. It's the sound. Mm-hmm. How much water is the system able to treat?
Recover from the membrane.
Oh, to recover. Okay, that's a great question. The water, right now, we are going by the RO or the membrane process. Like the recovery of water is still, we're having at 85-15%. That's where we're at. And with the process that we are instituting, we are pushing to increase that ratio from, much greater than 90. So that's why we're putting all these systems in together.
Okay, so thank you. So second question is, okay, so if you are operating at 90%, recovery or efficiency, so you are just generating 10% of the feed water, right, as a concentrate. So why did you not consider that concentrate directly sending to the destructor or the destruction technology? Was there any reason why you consider foam frac and then, then the destruction technology after that?
I think that's important. Did you get that? Okay. Why we didn't consider what?
So the concentrate that's coming from the membrane, right? You could have just sent it to the destruction, right?
I think without the mic is better.
Yeah, that's okay. So the part that's not recovered from the membrane, why didn't it go to the foam fractionation rather than like right to the destructive system?
That's a good question. Thank you. And again, I think it's the mic. So because the destruction technologies today still, they are very expensive. And by by reducing the volume and further concentrating the PFAS, what we are doing is lowering the capital for the destruction, right? So that's the principle of making sure that we are reducing and also eventually that we have less waste in the process. Without mic. Oh, without mic. Please, without mic.
Mic check, 1, 2, 1, 2. Is everybody good? Can we hear? Okay. My question is regarding, can you hear me?
Yes.
Okay,
Why yours is different?
Because of that one.
Oh, you fix it. Okay, thank you.
Good. My question is regarding the EBCT for the G400 versus the resin. Were they different? And what were they?
What they were different? Why?
What was each EBCT for the pure affinity versus the resin, and
Yes.
what were each of them?
So the pure affinity was it was in seconds. It was 0.3 to 0.5 minutes, and the ion exchange is typical. It's 3 to 5 minutes.
Let me try. So I like the concept that you guys use one system for everything. I just want to make a comment because you want to make all the money yourself. That's a good thing. We're all capitalists, right? So for the influent, where you take water in, do you have a criteria or a standard how much loading you have? I'm pretty sure you cannot treat leachate. That's like loaded with PFAS. What kind of, can you take wastewater treatment plant, affluent or influent, to reach that goal?
Eventually, we will get there, but this is designed solely for drinking water at this point.
That's what I thought, public water systems.
Yes.
Good.
Oh, that is fine.
Hi, we enjoyed your presentation. Can you explain further the enforcement letter that you said would be coming out before May 2029? And do you think that that is going to be affected at all by what's happening in the new administration?
That's a very good question, too. All right, so the enforcement letter is part of the April 10, 2024 drinking water standards. And what is going to happen is that utilities have had the opportunity to monitor and treat drinking water and remediate and have any type of treatment to be able to make sure that PFAS, there's no PFAS basically, because 4 ppts is basically no PFAS. So that's the idea. Once that happens, it becomes another water quality parameter that utilities have to monitor, just like E. coli, just like any other one, like lead and everything. And if there is an excursion, if there is not 4 ppts or it becomes 5 ppts, or there is immediately a notice of violation later being sent to the utilities. And as an NOV, utilities are obligated to send that, do a public notification, telling everybody that the system was found with PFAS, and then put it in the consumer confidence report at the end of the year. Yeah. So if that's going to change, most likely, and this is what I think, for the ones that have been promulgated, like that one, is not going to change. And even if that changes, let's say that one day we don't have EPA, who knows, and then we don't have anybody who's going to enforce it. States are still doing it. Like states have recognized that PFAS is a contaminant that can cause cancer, endocrinological disorders, obesity, there are so many things that can cause PFAS. And so it is already in our mind, it is already in the mind of the consumer, and that is part of the pressure that, okay, it is here. Litigations, we're here for the lawyers, that is here, and it is still, there are grounds to be able to continue. States really want to care for the constituencies, and they have instituted, even before EPA, very strict rules, like New Jersey did before EPA. EPA was at 70 PPTs, and then New Jersey was at 13. And everybody had to comply, right? And that can happen, I would say that will continue to happen with the states. And as I showed, for the other type of products, it's going to continue to happen with other things, like wastewater, like industrial water, like products made out of PFAS. And it's important to think about that and start to plan to how to remediate from this point until that happens, and also how to find alternatives to PFAS. So it's a great compound. It really has served us very well in other ways, but it's a bad compound in terms of health-wise. So an alternative will be fantastic.
Very good. Well, thank you very much, Doctor.
All right, that concludes our